Hello everyone, thank you for being here. I am Edoardo, I am the president of the MUNU chapter of IEEE Eta KNU, HKN. We are an association of Politecnico of Turin. Eta KNU is an honor society of IEEE, the Institute of Electrical and Electronics Engineering. It was founded in 1904, but our chapter was founded in 2017. In our association, we deal with many subjects are about IEEE, so electronics, informatics, computer science, data science, and many other subjects. So today we have some guests and then we will talk about quantum computing. That is a technology with a huge potential. And I leave the floor to Davide, our events division manager, and I will ask you an applause for events division and Davide, because in the last few months we had several events and they made a really good job. So thanks Davide, thanks events people, and thank you everyone, thank our guests, and please, Davide, continue. Thank you. Yeah.
Thank you, everyone. I'll be very quick. I just want to thank everyone. It's a pleasure to have you here. And I just want to say thanks to all the people who contributed to the organization of this event. I think it will be really cool to listen to experts from the quantum computing field. And I just hope that you enjoy the event. So we just leave the microphone to Edoardo, right? Yeah, to Edoardo. So thank you.
Thank you. Thank you very much, everybody. Thank you for being here. Thank you for taking the time to join us. My name is Edoardo Giusto. I'm a postdoctoral research assistant here at PoliTo in the Department of Control and Computer Engineering. And in here we have...
My name is Lorenzo Vergadano. I'm a master degree student in data science engineering here at PoliTo.
So today we're going to take your first step into the quantum journey. Why do we want to do this? Because in the next few years, quantum computing, communication, and technologies in general will be crucial. And we need to be ready. We need to start right now, avoiding in some years to come workforce shortage, which is today already something real, okay? How do we do this? By carrying forward dissemination and contamination events, keeping people interested in this, bringing people together in partnership, joining into research projects. So on the practical side, what do? We have worked very hard in the last few months to create two entities. One is EnTOngled, a citywide community, and the other one is QubiTo, a student team right here in PoliTo. So why QC? QC will be the next big thing, because quantum computers will be able to solve problems which are impractical for classical computers to solve. They just cannot fit, or they will take eras to solve. In domains such as simulation of systems, like drug discovery, battery technology, moleculars in general. And also in search, optimization, and deep learning activities for tasks such as fleet management or routing. governments are literally pouring money into research for this domain. Italy, not quite so much, unfortunately, as usual. This is an estimation of the public funding worldwide from 2010 to 2020. So on the public domain on the left, but also on the right you see the money raised by startups. Okay, it's growing at an impressive rate, and this is just more than 2 billion just for 2021 alone, just for the small startups and not the big players like IBM or Google. We couldn't have a presentation on quantum without quoting Richard Feynman, who is one of the founding fathers of quantum computing, probably the first one who theorized the use of the creation of a quantum computer. He thought, well, nature is not classical. So in his mind, it didn't make sense to simulate it using a machine which is digital. Okay, so we need to think actually very different in order to create a quantum computer. Unfortunately, he died, many years ago. As Giacomo will show later, we are working very hard and progressing very hard in this way. So what? We want you. We need you. We need you to join EnTOngled, which is this broader community on quantum-related topics. And this community will organize, for instance, hackathons and also competitions in order for the people to participate. So setting up events and giving support for the people who want to get involved. And also build connections among the entities involved in quantum, so setting up scientific or technical collaborations, research, let's say, oriented, and what we are doing actually right now. But it's also open to enthusiasts on this topic, despite the fact that they are not also already employed into some company working in that domain, or just people who know about quantum and want to share their knowledge.
Thank you, Eduardo. On the right, instead, there is the logo of QubiTo. QubiTo is the first official Polytechnics team related to quantum computing. Please make an applause. I'm joking. What we would like to do in QubiTo, we would like to also participate to hackathon in order to make some competition and make some challenge. The PoliTo students have the possibility to challenge themselves in this hackathon. Then we would like to organize event, not only the internal event inside the Polytechnics, but also with external entities. And then at the end, we can see that one of the most important words for our team, for our new team, is the heterogeneity. So no matter what is your background, your quantum computing knowledge levels, if you are interested, if you have the passion for this new kind of studies, you are welcome. Let me better explain who can participate inside QubiTo PoliTo teams. We didn't put some strong limitation regarding who can participate, but we would like just to express what is the topics that we'll address in our team. And there are computer science, physics, optimization, chemistry, and so and so. What you can see on these slides. So if you're interested in one of these subjects and you want to make a sort of challenge with yourself, you're welcome on QubiTo. This is the roadmap of QubiTo. From here, the date this year is the first year of QubiTo, and we start in September 2023 with some online hackathon. Then in autumn 2023, we start the team expansion steps and the website creation, networking, and especially the self-education sessions in which the team members self-learn inside the teams topics related to quantum computing. Then, in the winter 2023, we would like to participate to some European and Qiskit hackathon. And from winter 2024 until the summer, we would like to organize 3 main events. The first one with Intesa San Paolo, the second one with IBM, and the third one with Quantinium. Of course, at the end, we would like to participate to other hackathons. Okay, here you can see some of the companies or entities that build the quantum ecosystem here in Turin. If you don't see your company here or your association, don't worry, you can get in touch with us and we can enlarge the community, because this is our scope, as Eduardo mentioned before. Okay, so the last but not the least, you can see here the 2 QR code. The first one with EnTOngled community, the Telegram groups. I recall you that this is the free groups based on Turin, in which you can participate and join inside the team. And on the right, the QubiTo QR code in order to apply, because I remember that this is a PoliTo team, and you have to apply in order to participate. Don't worry, you can see this QR code also on the post-it attached on the wall. Thank you very much for your attention.
Okay, so let's start our journey with quantum. So, good afternoon, everyone. I'm Giacomo Ranieri. I'm a software engineer, or quantum software engineer at Intesa San Paolo. And today I will introduce you to the quantum computing, hoping that you don't know it. Otherwise, probably you will be pretty annoyed by me. Okay. So in the next 30 minutes or so, I will introduce you to the world of quantum computing, starting from why we need quantum computing and what are the current limits that we want to address with it, and something has been already said. And then we will have a look at the principle that quantum computing is leveraging on, and how make it so special. And then we will see a brief panorama on the hardware and the main model of quantum computation. We will then see how we can use quantum computer nowadays, and finally, why is important for us at Intesa San Paolo. Sbagliato io. Okay, so why quantum computing? Well, let's begin with why do we need quantum computing. So there are types of problems that are impossible for current traditional computers, even for the strongest one. They are impossible in terms of many different things. In this case, I can tell you that they are impossible in terms of long execution time, in respect to the time needed from the business, maybe. For example, when you try to decompose an integer number in its prime factor, independently from the number of digits, it takes a huge time. And when you try to forecast a financial scenario, when the market is still open, probably you won't be able to do it. You will need to let the market close and then simulate it. And this, of course, is pretty inefficient. Or maybe they are impossible in terms of unsatisfactory quality of the solution. For example, when you try to simulate a drug compound, or when you try to find the solution to optimize a financial portfolio, trying to both maximize the revenue and minimize the volatility at the same time. Imparerò mai? So, but why is not possible to solve these problems with the current computational paradigm? Well, there are three main points that are stopping the progress of classical computing. The first one is the chip miniaturization. You probably have heard already about Moore's law. It has defined until now the technological progress of chips. It says that every 2 years, the number of transistors inside a defined dimension of chip will double. Well, this is no longer true. We are reaching a physical limit where beyond that, you are going to a subatomic particle, which are more acquainted to quantum physics than classical physics. The second one is the space complexity. Solving some problems mean that you need a lot of space, a lot of memory space to put the data inside the solver. Well, this is no longer possible for certain type of application with classical storage architecture. Take, for example, the caffeine molecule. The caffeine molecule, you need 10 to the 48 bits. So try to imagine 10 to the 48, 10 with 48 zeros of data to store it. Well, this is roughly a data center big as the surface of the moon. So take that in consideration. And then, of course, there's the time complexity. There are problems that haven't got yet found a deterministic algorithm that can solve them in polynomial time. So if you add more variables, if you enhance the quality, the time for the resolution is exponential. And that's bring it to quite impossible to solve them. So we're starting to get a point in what are the limitations. So what are the standard computer different from quantum computers? So standard computer use the classical physics and a deterministic approach. For each input, there is a given solution. Quantum computer use quantum mechanics, of course, and its approach is probabilistic. So you won't have always the same solution. You have a probability to find a solution and another one. There are many technologies in quantum hardware, and only one in the classical standard computer. That means that maybe quantum computer in future may have different type of stable technologies that can solve better problems than other ones, giving a space for different type of application on different type of quantum computer. The problem of quantum computing is that nowadays, and probably will remain, with a fragile coherence of elaboration. Fragile coherence of elaboration means a complex error correction. And that probably will be always a problem for quantum computing, but not an insolvable problem. There are already a lot of error correction algorithms that are working, and they are studying more on that. But why is so special? Why quantum computing? Well, quantum computing has some principle based on quantum mechanics that make it so special for us. We have the superposition. Superposition means that you have a particle, a photon and an electron. There is not just black and white. It's not 1 or 0. It can be more than one state at the same time. Don't know if you remember the Schrödinger paradox. The cat in a box with a bottle of poison. If you observe it, you don't know if the cat is still alive or not, unless you open the box. So if you don't know if it's still alive or dead, it is both at the same time. From your perspective, it's both alive and dead. And then we have another important principle that is entanglement. Two or more particles can be entangled with each other using particular operation, of course. When those particles are entangled, an operation on one of them influences the others. And if you manage to master this technique, by observing just one particle, you can infer part of the information of the other, leading you to the possibility of continuing to elaborate with these other particles by not destroying their state, and destroying just the state of one of these particles. And adapt maybe the algorithm based on that. And finally, we have the interference. Usually when you execute a quantum program, or a program in general, you desire to find a solution to a problem. Otherwise, you wouldn't use it. Maybe there are more than one solution. And by building destructive and constructive interference, using the many operations available in quantum computers, you are able to amplify the probability to find the result you want and diminish the one of the result that you don't want. By building with all these principles together, you construct your algorithm, your quantum algorithm. Well, what's then the information unit using quantum computing? Is the qubit. There's a lot of fantasy in that. It's only 0 or it's not only 0 or 1 like the classical bit. As we said, there is a superposition, so it can be both 0 and 1 at the same time. 0 with a probability alpha in this case, or 1 in probability beta in this case, also in this case. Usually you represent it inside a block sphere, which in this case, this state is a vector of length 1 that starts from the center, the red one. And is described by two angles, theta and phi. The first one, theta, which is directly correlated to alpha and beta, our probability amplitude. And the other one is the phase of the status. Well, so what happens if we add more than one bit and more than one qubit? Let's pick 3 as an example. With 3 bits, we can simulate, we can configure it on just one state, for example, 101. But with 3 qubits, we can use all the states at the same time. We got 8 simultaneous configurations, each with a probability alpha 1, alpha 2, of being observed in the quantum computer. These allow us to add a huge amount of data stored inside the quantum computer, allowing, for example, the caffeine molecule that we talked about earlier. Now that we've seen the magic behind the quantum computer, let's see how they are built, how the major hardware technologies have come to us. So we have, for example, the superconductive. Superconductive means using, of course, a superconductive material. This material allows an extremely fast and easily scalable quantum computer. But to be able to use their superconductive capabilities, we need to cool them down to almost 0 Kelvin, like the absolute 0. You need 14 millikelvin, as far as I remember. In the picture, you see a lot of wires, and usually they are inside a cylinder. This is just to cool down the chip. The chip is like you can put it on a finger. But all of that is needed to cool down it to almost 0 Kelvin. Unfortunately, superconductive technologies has a reduced coherence. So you get speed, but unfortunately you don't get coherence nowadays. Main vendor for this type of QC are IBM, Google, and D-Wave, for example. Then we have trapped ions. Like the name suggested, they use the ions that are trapped using lasers or magnetic field. Trapped ions are extremely stable and have an highly coupling rate. So it means that many qubits can be entangled to each other more easily. So you can leverage a lot of this principle. But unfortunately, they are less scalable. Since they use a charged atom, they can't be tightly packed. You can't put them near one to the other. You need a building, an entire building, and usually like 1,000 of square meter to have a pretty decent quantum computer with trapped ions. And of course, all the lasers consume a lot of energy to trap these ions. Unfortunately, they have also a low instruction number per second, so you can't execute many operations inside the same space. But having there being there extremely stable, it's okay that you can still achieve a pretty good algorithm in the time you have. Then we have the photonic that, as the name suggested, use the photons running inside a silicon circuit usually. They don't require particular environment requirements, so you can put it just in a server rack inside your farm. They are highly reliable since they work with photons. But unfortunately, they have a non-universal set of gates, and their output digitization is complex. But they are working on that with new technologies. They are leveraging different parts of photons to be able to overcome some of these possibilities, of these problems. For example, Candela and PsiQuantum are one of the most important companies that are working with photonic computer. Then we have neutral atoms, parents or siblings of trapped ions. They use neutral atoms instead of charged atoms, so they can be tightly packed together, meaning they can easily scale, but maintaining the same high coupling rate and the same extremely stable. Unfortunately, to trap them, you have to use ultra-high vacuum, but still should be easier than bringing down to 0 Kelvin. Unfortunately, the drawback of trapped ions is still there. You can't put too many operations one to the other. It will take a longer time. And then we have other technologies that are still under studies at their early stages, like the silicon quantum dot, the same that are in the television, and topological qubit, for example, which should be the holy grail of quantum computing, if they even reach to build one. Many important companies are working on these type of fields. So we have talked about the hardware, but quantum computing has also two paradigms to program them, to work with them. These two paradigms are gate-based quantum computing and quantum annealing. Gate-based quantum computing use gates. This type of quantum computer are like an extension of the universal Turing machine, are more similar to our classical CPU. But they are the newer one. They are here from 6 years only, and they are not yet mature, of course. They could guarantee even exponential speed up in some type of application with respect of the classical computation. So that means, for example, that with the Shor algorithm, you can solve in polynomial time the integer factorization that we spoke about earlier. They are feasible with all the technologies we've seen so far. And to write a program for them, you write a so-called quantum circuit, mixing gate with different qubits and building your algorithm. And then we have the quantum annealing or analog quantum computing. it's a bit different from the other one, of course. It's specialized on a certain type of application, which are optimization problem, even though that if you can express a problem, any problem, as a minimization problem, you can solve it. So basically, should be universal. But probably it won't be the best solution to use always a quantum annealer. They are available since more than 10 years ago, and of course, they are more stable right now. Unfortunately, they give at most a quadratic speedup. And the technology that you can use to make them are almost only superconductive and photons. This type of quantum computer works by defining the minimization problem and putting it in a Hamiltonian matrix. This Hamiltonian matrix is then written inside the hardware, is encoded into the hardware, and we let the hardware evolve following the Schrödinger equation. So that at the end, we found a ground state which will hold our solution to the problem. Ground state is a minimum state, so we found our minimization. We found our minimum in the minimization problem. So how can we use this quantum computer then? We said that with the annealing, we build a matrix, which is almost more mathematics than other, and put it in the quantum computer and allow it to evolve. But with the gate model-based quantum computer, we write algorithms in terms of circuit. And we have three main ways to build them. We can use SDK, like the IBM Circ, the IBM Qiskit, the Google Circ, or Quantinuum tickets, which are all written in Python in this case, and expose to you classes and operation to allow us to compose your quantum circuit and then send it to the machine. But also exist other type of SDK that use like C or C++, for example. We have also languages made especially for quantum computing, like Microsoft Q# or IBM OpenCosmos. The first one being an higher level languages, and the other one being a low level languages, equivalent to the assembly of the classical computing, that is intended to be an intermediate representation between what you write in SDK or in other languages and the machine. Then we can use platforms that abstract us from the hardware and the SDKs. We can use something like Orchestra that allow you to write with their own SDK and decline it to all the other one and run it on different hardware. Or you can use the classic platform, which allow you to write the algorithm in a more functional way at an even higher level and synthesize it in form of Q# or OpenCAS code. So now that we know almost how they work, how they are made, how you can program them, then what you do with them? You do a lot of research, of course. You need to do a lot of research because even if we are at an early stage, we should not ignore quantum computer. Instead, we should use our valuable time to get to know them and how to exploit them in the future. So a lot of research, a lot of basic research, starting from the base algorithm or the hardware, going to the industrial research on how to apply these algorithms to more concrete problems, like financial, chemistry, and logistics problem, and many others. If possible, when we have these algorithms during our industrial research, we should build proof of concept, which are important to test the validity of our algorithm with the real data, maybe a small set of data, since the nowadays current quantum computers are not able to address many information at the same time, and see if they can scale when the hardware will be ready. And of course, if you are in a company, this POC allow us to create engagement within the business so that they maybe spend a little bit more money on studying quantum computers and quantum science. An hybrid approach is currently possible and probably will be always the solution. You have a problem, you segment it into different sub-problems, and some of them you can write in quantum, maybe connecting them to each other to create a bigger portion of a quantum algorithm. And that will lead us to a vast usage of quantum computer, of course. Some of these algorithms, like the optimization one, they are built for quantum annealing, can be production ready even today. There are companies that are building algorithms for quantum annealers. They have it in production right now. They use it on a daily basis for their optimization problem, like the logistic optimization or so on. So we need to be prepared for what's coming. Now, let's just see a little bit of how the financial industry is interested in quantum. Financial advisors like McKinsey and the Boston Consulting Group estimate that the finance will be the market, the industry, that will benefit the most of quantum computing. 30% of the hypothetical money spent on quantum computing will be on finance. So that means that for a financial company like us, it's much important. We can use it to solve a problem of the class of the scenario simulation and the problem modeling. So like derivative pricing, when you want to price a market object, or when you want to forecast the trend of market and stock. In all these cases, the ability of the quantum computer to simulate the interaction between many variables comes easy to be more efficient and accurate. Or we can use it for the solution and process optimization, like we also said before. Dynamic portfolio optimization and feature selection are one of the examples. And that's because with quantum annealing, we can easily find the best solution or process among many. And then we have the analysis of large and unstructured data, so big data. Big data can benefit from the capabilities of quantum to encode more of this data inside the quantum computer and find correlation, understand this data faster and more accurately than the current calculators. That means that we can tackle problems like the real-time fraud detection or the financial crime prevention. And these are just some of the problems that a company like Intesa San Paolo can use quantum computing on. So let's end with an actual application. Intesa San Paolo, in collaboration with the Politecnico di Torino and IBM, has published recently an industrial research paper on an important journal about a financial use case, of course. This financial use case is called the economic capital estimation, which is a model, multi-factor, with finite granularity. We wanted to enhance this model in terms of quality and simulation of it, and increase the granularity of these counterparties. In our solution to the problem, we created it with the fault-tolerant quantum computing in mind. So we created for the future, like I said before. We we took the work already developed by IBM, and we added features that were not inside of this work. They were new to the world. And using technique like the amplitude estimation, instead of the classical Monte Carlo used in the traditional calculation of this type of problem, we've reached an hypothetical quadratic speedup in terms of the execution time that allow us to have a finer granularity, but maintaining at the same time the same, if not better, execution time. So this is what industrial research and the use of quantum computing means. So I am now at the end of my presentation, so thank you for your attention. I hope I haven't annoyed you too much. It's been a pleasure for me. If you have any questions, feel free to ask.
Hi, can you hear me? Yeah. Thanks, Giacomo, for the presentation. I wanted to ask, since you have an insight in terms of finance and whatever comes with it, I just wanted to know, like, these research works, are they applicable right now in the finance field as they are for the moment, or they're still toy models which, let's say, push towards being applied in the industry? Like, can they be used right now?
In this case, this is more like a toy model. That's because to exploit this type of use case for a real scenario, we would need something like in the order of the more than 10,000 qubits. But there are other works that are going to be published soon from our side that we haven't the business on board yet, but they are already usable. You can use them for their purpose. We are talking about, in this case, the financial portfolio optimization. You can actually optimize a portfolio with that.
Hi, thank you for the presentation. I'd like to ask, as a quantum algorithm developer in Intesa, what language or SDK do you use in your everyday work?
Interesting question. We have different approaches since we're working with different partners. But our main focus are on the Qiskit from IBM. And since we are working together with the classic team, we are working with their platform. So we are building a higher level representation of the algorithms in a form which is still using Python, but using a more functional approach now, as I said before, to build our new toy model. So I can confirm you that we are using this too at the moment.
Hi. I have a friend of mine that told me that nowadays he is working on a quantum algorithm, and he said that this quantum algorithm it's not only for a quantum computer, but even for a normal type of problem and a normal type of computer. I don't know if this is true or not, but
well, probably it was meaning it was talking about simulation, because you can simulate up to 40 qubits with a pretty good hardware. In terms of usually use GPU for 40 qubits. But I don't know what it was meaning with classical problems. Well, they are an extension of the quantum of the universal Turing machine. They could be used to do the same stuff as a classical computer, but it's like going from here to your home, probably a few kilometers, but with a rocket instead of with your foot or by car. Using quantum computer in our smartphone, probably it would be necessary would be necessary. They maybe will be put inside the data center of the companies, or even stay in the cloud, like IBM is doing right now, or all the others. So they are building their quantum computer and they're making it available through the cloud, to the cloud.
Hi. It has been said that Italy hasn't invested as much in quantum as other countries. And for example, how much has Intesa invested in such field?
Let's say is less than I would, but I can't tell you how much.
I wasn't
Unfortunately, I can tell you that we are in the plan for these industrial terms.
Okay.
For in this 4 year, Intesa San Paolo has committed to push on quantum,
Okay.
but I can't tell you how much.
Oh yeah, I wasn't looking for an actual number, like in general
I'm
terms.
sorry. I'm sorry for that.
No, thank you.
Hi. Is there any possibility to hack blockchains with using quantum computers?
Well, theoretically, yes, because as far as I remember, it's still based on part of the algorithm that can be brute forced, probably by by the hardware in the future. But I think they are trying, of course, as the industry in general are trying to mitigate the problem by creating new algorithms and so on. Probably it would be the same for the blockchain and other sensible parts of our ecosystem.
Oh, okay. So one day everything will be hackable, I guess.
Well, everything will be hackable if the problem in which they rely, the difficulty of the problem that make them unfeasible to hack, will be tackled by a quantum computer. So, like the problem of the integer factorization. We know that RSA algorithms and others also use these type of problems to achieve their security. But being in the future constructed quantum computer that will be enough strong to be capable to solve this problem, they will leave these type of algorithms pretty ineffective, and we will need new algorithms that can't be, and there are times this type that can't be hacked by a quantum computer. We are talking about like homomorphic cryptography, which is quantum safe. So, for example, recently, as far as I remember, last year, the US stated that they chosen one of the new algorithms that will be used for the public key encryption that is made by IBM and is quantum safe.
Okay, we have a question from home. Federico Tibias asks, as far as I have understood, a quadratic speedup is still fairly limited. Do you know if there are any applications in finance that are able to obtain an exponential speedup?
As far as the current research topic, I'm not aware of something that is going to have an exponential speedup. Of course, a quadratic speedup is not the best thing you can have, let's say. But in terms of problems that you can already solve, but you want to solve it better, a quadratic speedup will allow you to solve it with the same time, but with a better quality of the solution, probably. And that is still a valuable business model.
Hi, Giacomo. Just
Hi.
a curiosity. So far in your company, do you have any active project totally based on quantum? How many? Or
we have a couple of use cases. There are fully quantum. One in which I'm working with Francesca. One of which I'm working with Politecnico and Emanuele. And other one that we are working with other companies. So we in our team are pretty committed with the quantum, and we believe in it. So we are going full quantum.
Okay, thank you. I have one question about what is the highest capacity that we have in terms of qubits in currently quantum computers, and is there some kind of Moore's law for quantum computers that, for instance, we expect that the number of qubits is going to be double each 2 years or not?
That's an interesting question. Unfortunately, I don't. There is no one that has nowadays being a prophet on quantum and the number of bits that will be in the future with some kind of formula. Since they are going in a path that is not yet defined, it is still at an early stages, and is making sometimes baby step, sometimes big step. For example, in just a couple of years, IBM has gone from 27 qubit to 4033 qubits. And for their type of computing, which is gate model-based quantum computing, this is the biggest number of qubits you can have. Instead, for the other type of computation, which is the analog quantum computing or quantum annealing, we have reached around 5,000 qubits, as far as I remember. But since they use different type of encoding, they cannot relate one to the other. You can solve the Shor algorithms with those 5,000 qubits, but you can solve it for a small integer with the 40,033 qubits that are available on the IBM machine.
Okay, thank you.
You're welcome.
Just a fun fact, we mentioned Moore's law, and Gordon Moore has been one of the HKN members in the past. So maybe next prophet of quantum computing law could be one of HKN.
Could be coming from...
I don't know if it could be one of our chapter, maybe one of another chapter, so...
Maybe someone who from the chapter goes to the IEEE.
I don't know, maybe. We will know.
Observe and then make your prediction.Maybe it will become the next Moore's law.
Hello, thank you for the presentation. I want to ask you, how are you facing with decoherence and error correction problems, fluctuations, and the reliability of the system when you are using so many data, and we know that decoherence is strictly correlated with the input we are using. Are you working with an higher level, working on algorithms, or we are also working in a lower level with circuits and design of a certain kind? Thank you.
Well, we are not focused on error correction, since this is more like an academic research problem than an industrial research problem. So we work mostly at an higher level. Of course, we have to consider the problem and maybe try to encode our data with in the more efficient and the less prone to problems way. There are many types of encoding you can use for the data. Some are more coherent, some other are not. Of course, your job, our job of building an algorithm for an industrial use case is also using the best sub-algorithms that we can have.
Thanks for the presentation. I'd like to ask the question about so far, like whatever we have heard about quantum computers, it's all about like potential, more of potential rather than something that is in the status quo. So I'd like to ask, what is the one thing or things that our researchers in quantum computing are putting their hopes on, so that in the future it will really work out? What I have heard so far is was about like our classical computers were also in that state, in the state that quantum computers are right now. So maybe in the future we'll have something better. So what I want to hear is it about the problems that we have about quantum computers, the noise and all the stuff? Is it all about like ingenuity, that we're not really able to come up with something more ingenious, or is it about like problem that is like far more about physics and something else?
Well, this type of things you're meaning are more hardware related. So the big question is this is a big question. Of course, maybe at the beginning you are a little more used to ingenuity, and when you have your first approach. But then when you try to scale it, of course you find all the problems, the engineering problems, because we know the physics behind that. But it's becoming more of an engineering problem to put more qubits, to entangle them better, to use the correct technology to construct your quantum computer. Nowadays, it's more like an engineering problem. And us as a researcher in the quantum computing field, on the side of the software, we need to think about the future when this will not be a problem. It won't be our problem. Someone else will have solved it on the hardware, or in some kind of middleware, where we don't have to deal with it. Like in the classical computer, we don't deal with the error correction, but it's still done. We don't know how, because we completely forgotten that there is error correction inside classical computers.
Thank you.
Thank you very much. Thank you very much for having me.
Okay, thank you for your questions. I've seen a lot of interest in all of you, so it's really cool. I will give now the microphone to Professor Bartolomeo Montrucchio. So an applause.
Thank you very much. And at first, thank you very much to Eta Kappa Nu for organizing this meeting, because it was very interesting. I am very happy to have here all these people. And so just a few words about didactics, because you will hear later something about research. You will have also answers to your questions, because we are also working on research, both from the electronic point of view and from the software point of view. But in a couple of minutes, I will very briefly tell you which are the didactic point of view of Politecnico. Okay, probably you know, for sure you know, we are going to launch a new master degree, second level, therefore, and this will be in quantum engineering. Our purpose will be to, of course, have the second degree level, and it will cover all the aspects required for quantum. So not only the software or the hardware, because today we are dealing about on quantum, basically on quantum computing, but the quantum world is not only quantum computing, there is also quantum communication, that is the other side. And it's very important because, of course, in the future we will expect to have a quantum internet. And the quantum internet will be constituted by quantum computers and quantum communication together. And also another aspect that is very interesting, that is quantum sensing. So to build new sensors which use quantum principles. That is extremely important and useful. All this stuff will be inside this new degree, of course. This is an advertisement. Okay? And just for maybe for your interest, we have already done once a master, in the sense, the Italian meaning of master, that is of course it is after the second level degree in quantum communication and computing. That is now at the second. We are going to launch in the next days the second edition, and of course is for people that maybe is already working in some companies, and of course they are not interested to get a new degree. They are basically interested in getting some specific competencies. We can also provide single courses, because maybe some companies interested in formation. Because the main problem in quantum is that, again, I am very happy that you are here, because the main problem is that in this moment we are lacking on this. For example, I'm not a physicist. I am at the beginning I was an electronic engineer, and in fact I know basically nothing on physics. And this means that I had, when I started working on quantum, to learn a lot of things about quantum mechanics and so on, because it was very, very useful, very important. Of course, from my point of view, like an engineer, I am waiting for the moment in which it will no more required to know quantum mechanics to use a quantum computer, because as it's been told just before, of course, the basic idea is that today we don't know actually how is built a classic computer. Okay, the so-called threshold theorem, that is the one that demonstrates that a quantum computer can be built, exists also for the classic computers. Okay, it was developed by von Neumann a lot of years ago, but no one knows that it exists, because it is considered as normal that a classic computer works. It works, and that's all. Okay, so I am waiting for the moment in which the quantum computer will work, even if we don't know how it works. Okay, and basically I finished my slot. If there is some question about didactics, thank you very much, and I will leave the.
Okay, thank you very much again. I will give now the microphone to the research groups Darwin and Links, and that will present the research topics.
Okay. On the other sense. Okay, so good afternoon, everyone. I'm Chiara Vercellino. I'm a researcher at Links Foundation, but also a PhD student at Politecnico di Torino. So I'm just in I'm kind of superposition of working positions. Anyway, in this moment, I will talk to you about activities that we have in quantum computing at Links. Links Foundation is a research center. We are based here in Turin, so we're also part of the EnTOngled community. And we are really close to Politecnico, and we collaborate a lot with them. In the slides, there is all the team that works on quantum computing in Links. As you can see, we have very different backgrounds, as also this was another important point in the presentation of the communities. You see that I'm mathematicians, but my colleagues are physicists or computer engineering, so really, really different backgrounds. And Olivier Terzo is our head of area, and Giacomo Vitali is the person you should contact if you want to get in contact with us. Maybe if you're interested in doing some internship or go for some thesis proposal. We have some proposal on our website. We have a lot of activities, and I cannot use this. But I will focus on the two most importance. We have research activities on neutral atoms. we are in close contact with Pascal and QERA, which are the two of the main players on this technology. Pascal is European, QERA is an American instead. They are a spin-off of MIT and Harvard. And we investigated a lot their technologies, and we also came up with a few publications that are a really nice achievement for us. And this one in particular is a way in which we started from an industrial optimization problem. Then we had to map into a combinatorial graph optimization problem, because this is the kind of problems that are most suitable to be targeted by this kind of hardware, because basically you have to represent graphs onto the quantum register to be able to solve optimization problems on this machine. And so this is one of the research we are doing. Still in the optimization field, but with another technologies. In this case, we are working with quantum annealers. In this case, the reference hardware is D-Wave, and one of the main outcomes was coming from a collaboration with Politecnico di Torino and a team, which bring their own use case. Was about an optimization problems to assign a principal cell identifier, and in this case, to work on the wave quantum machine, you had to formulate the optimization problems in a QuBo form, that is, stands for quadratic, unconstrained, and binary, then DO just for optimization. And so you have to start from the industrial problem, build a quadratic matrix with the penalty stairs and the objective function, and then minimize the objective function that is in the form of a quadratic problem. And we did the same thing also for other problems, for instance, protein folding, job skiddering, and best path pollution. And but we can do with a lot of other problems. Just the major work is, this case, is for the formulation, so in the mathematical modeling of the problems. And with that, I just switch to my colleagues in Darwin.
Thank you, Chiara. So I'm Emanuele Dri. I'm a PhD student at the Department of Control and Engineering. Thank you. And here you see the first line of Darwin with the PhD student, myself, Marco Russo, Nicola Di Lillo, Antonio Marceddu, Pietro Chiavassa, and then second line with our postdoc Edoardo Giusto, and higher in the, let's say, chain of command, Filippo Gandino, Renato Ferrero, and of course Bartolomeo Montrucchio, you heard about. He talked before. So we work with IBM, with Intesa San Paolo, with TIM. By the way, with TIM we have a work on some quantum-inspired algorithm. Probably there was a question related to this before. So an algorithm for classical computers inspired by quantum principles. So could be an answer also for someone of you before. And we focus mainly on 3 directions. And of course, I have to mention, we also work with the friends of Links, and Chiara, who spoke before me, and Giacomo are also PhD students at Darwin. We focus on 3 directions: quantum machine learning, simulations and control, quantum fault injection, and the application of quantum computing to finance. Of course, I'm not going to talk in details about finance, because it's related to what Giacomo described before, and so this is what we do in collaboration with Intesa San Paolo and IBM. But I can give you some more details on the other 2 directions. So starting from the first one, quantum machine learning, quantum simulation, and quantum control, you can see the colleagues that are focusing on this task. Let's start with quantum machine learning. So we have essentially different kind of quantum machine learning. We have to distinguish when we talk about them. In this case, we are focusing on, let's say, quantum machine learning on classical data, okay? So the data is classical, the algorithm is a quantum algorithm, okay? In this sense, we have, for example, variational quantum eigensolver. We can think about them as the analogus of neural networks for the classical domain, but of course we are talking about the quantum domain, and quantum feature kernels. And where are the advantages? For example, with quantum feature kernels, we can exploit quantum computing to bring our data, our classical data, into exponential future space, okay? And perform there the calculations, solve the problem, and achieve the best solution that we are looking for. Of course, this can be done classically, but classically we need the complexity is also exponential, while with quantum computing, it's linear. So you can see there is an advantage, of course, given that there are constraints in the number of qubits. You already heard about them. This group uses mainly two technologies. You heard about them before. Neutral atoms. The advantage is a high degree of connectivity. So if you want to entangle many qubits, you can do so without having to, let's say, make the depth of the circuit explode. So you have to imagine that if we have limited connectivity, we need something called swap gates in order to, let's say, have communication between qubits that are not near physically on the chip. In this case, this is less of a problem, but there are other problems with neutral atoms, other limitations. Giacomo mentioned before some of them. I would say that in general it's a less mature technology. So there is still a lot of development that need to be done in order to further improve this technology. Something more mature is superconducting qubits, still not perfect, but let's say higher degree of maturity. They are faster. They are, let's say, easily usable if you want to just remain on a slightly higher level and define your algorithm and run it on the machine. But of course, they have limited connectivity. So we keep all these, both the domains, in order to, let's say, take the best from each one. The next step is quantum simulation. Again, this group is working on experiments and methods that require the use of linear optical circuits that manipulate photons. Again, a possible application here, weak measurement. Essentially, we are talking about non-destructive measurement of a qubit. So imagine you can partially measure a qubit without completely destroying its wave function, collapsing its wave function. So it's something really exotic. And let's say that it is possible to simulate this experiment with a quantum computer, even a non-photonic one, so superconducting or neutral atoms, etc. And the same quantum phenomena still happen as a result. So it's quite interesting, something really, really quantum, and they are working also on that. And finally, quantum control. So you heard about gates, and for superconducting qubits, we heard about gates a lot, but what are gates? What are these gates? So essentially, they are pulses, okay? Microwave pulses, and the parameters of these pulses depend on the desired operation, okay? So, of course, we will need a control system that allows us to precisely and in an optimal way manipulate each qubit. This is very important because essentially allows us to perform the operation that build up our algorithm. Usually in this field we talk about geometric control that is based on differential geometry. I'm not going into details, I'm not able to. But this is what is used usually. But we have to keep in mind that the control hardware used is very resource limited. You have to think about FPGA, so something that is not really that powerful. And pure geometric control is computationally hard. So you can see there is a problem there. As any good problem, a good engineer tries to find a solution or a workaround. And so they use machine learning together with geometric control to optimize the performance of this task. This was the first direction. Quickly, second direction, I won't talk about the third, that's quantum finance, that was already discussed before. So the last one from my side is quantum fault injection. Here we are closer to the hardware in a certain sense. In fact, we deal with stochastic noise, something that affects qubits. It is not just the simple decoherence that you can count off. Essentially, if the circuit is too long, there is decoherence, okay? But stochastic noise is something different. Usually, the main source of this noise is cosmic rays, which decay into high-energy neutron, but also that can act on transistor for classical computation. This was a problem also for classical computing. It's solved now. But also gamma rays, electrons, that unfortunately, pions, muons, neutrinos, that unfortunately all act on superconducting qubits. So with classical computation, we only care about high-energy neutrons. With quantum computing, we care about all these particles. This is a problem. Because, of course, we have an impact. This is from a paper by Google on their machine, the Google Sycamore, which is a 10 millimeters by 10 millimeters chip with 25 qubits. They bombarded the chip with these particles. They observed a fault duration of 25 milliseconds. And this is order of magnitude longer than single execution for a quantum circuit. So you can see that it's something that lasts longer than the duration of the execution on the quantum circuit. And these events happened independently around every 10 seconds. So this is something that is scary if you want to reliably use quantum computers. So what happens essentially, you can see the physics here, essentially there is a charge that of course gets deposited from the particle on the substrate of the chip. This charge breaks the Cooper pairs. If someone of you is familiar with superconductivity, Cooper pairs are what allow for superconductivity. And this excites the qubit, and so there is a shift. So you saw before the Bloch sphere that represents the state of the qubit. You can imagine that the state changes on the sphere. This is a problem. How can we deal with this problem? There are several proposals. Our group focused on looking for a way, firstly, to simulate this phenomenon. So build a quantum fault injector able to simulate the effect of transient faults, and then try to see which are the effects for different kind of quantum computing application. So quantum machine learning, circuit cutting, which is another technique that is quite popular recently in quantum computing. And essentially now we are in the process of trying to design solutions, okay? So to mitigate at least the effects of transient faults. That's all from my part. Of course, we have thesis proposals. If any one of you is interested, you can contact us, and me or Eduardo. And yeah, that's all, I think.
Okay, thank you. If you don't have any questions, we can pass to the next speakers. And last but not least, they will present their research topics. So thank you.
So good evening, everyone. Thank you for being here in this event, and thank you to ETA for organizing this important moment for discussing about a hot topic like quantum computing. I think that we are the last group presenting today, and so I can joke about this, saying that there's one more thing to say today. And I'm Andrea Marchesin from the Department of Electronics and Telecommunications. And today I'm here with my colleague, another PhD student, Antonio Tudisco, and we will present you some of the research topics that we addressed during the last years in our research group. But first, we want to present you our team, starting from the professors of our research group. For those of you who are electronics engineering students, you should have met some of them. We have Professor Zamboni, Professor Graziano, and Turvani and Gianluca Piccinini. And then, in terms of PhD students, our group is composed by 5 people. Me and Antonio are part of them. But we want to mention also all the people that helped us in our research during the past years, starting from Giovanni Cirillo, a former PhD student of our group, and then all the thesis students that had the possibility to work on our research topics and contribute to the publications that we could achieve in those years. This is a slide that is a sort of timeline of the different research topic that we addressed when we start in particular. In these years, we had the possibility to deepen a wide range of topics in this specific research domain. Again, you can see the different people that joined the group and contribute to the different works. So, so an overview of what we do. As we said before, and the other speakers told you, the research domain of quantum computing today is very broad because there are a lot of open problems, starting from the hardware perspective, so the physical layer, how we build our quantum computers, but also growing up to higher abstraction layers. We know that we have to define software tool chains also to manage these hardware solutions, and we have also to explore possible applications. So we have different abstraction layers, and we covered all of them during this year. And we want to present you very briefly the main results that we achieved in our explorations. Also, in this context of quantum computing, there's the need, as we said before, to define a sort of tool chain where we can have a backend, so a physical machine or software simulators to implement our quantum computing algorithms. We have to define a software layer to compile what we want to implement on these machines, but it's an essential part that can be found in every application, also in electronics engineering and computer science domain. And then at the highest level, we have the applications. So we want to explore different possible research topics and find the opportunity of quantum in them. And in order to implement possible solutions, we need also to have a software stack again, but which is useful to give a form of our algorithms. And so the need of software libraries are needed to help us developing quantum algorithms. Starting from the lowest level, we developed in these years quantum computing hardware simulators. What does it mean? When we have to implement a quantum algorithm, we have different possible choices. We can implement them on real quantum computers, but this is not typically affordable. And maybe it's not, it's neither feasible, because the limited hardware resources of the actual quantum computers don't allow us to implement really complex algorithms. Therefore, what we need in this context is to define simulators, both considering the noise, so the real problems that affect quantum computers, and also the most ideal ones, so for providing fast solutions to our quantum algorithms, speeding up the possibility to develop to the development phase. So we have defined two kinds of simulators. One that is ideal, and this allowed us to evaluate the advantages of exploiting particular strategies in quantum computing, keeping the focus on the performance of this software simulator. We had also the possibility to compare the results achieved by our tool with the state-of-the-art ones, and in some cases we obtained good results. But great effort is put in developing the noisy one, and you can understand easily why. Because the actual quantum computers are not ideal. They suffer from a lot of non-idealities, like noise. In a previous question, we discussed about the problem of decoherence. And we have to develop, and we did it, a software simulator to try to implement a quantum algorithm on a classical machine that can get back the results that also real quantum computers can get. And the reason, the most important reason about this need is that we don't have to access a real quantum computer. Therefore, working on local machines is essentially more fast, more convenient. And we have had different models addressing different technologies, and they are reported in this slide. For what concerns the quantum communication, we tried to adopt the same methodology in simulating quantum computers, also to simulate quantum photonic systems to simulate quantum communications, and in particular addressing the QKD BB84 protocol, that is the most famous one. Again, we developed two different simulators. One more linked to what we call coherent states. And for those of you who are interested in physics, we have developed models for photon polarization encoders, pocket cells, beam splitters, and other elements that typically are adopted to implement experiments on quantum communication systems. What we are doing now is to abstract this infrastructure, widening also the application perspectives in order to put the previous quantum computer simulator and this simulator for quantum computer together. And this is useful when we have to design and to prototype quantum computing systems can bring together both the computational part and the communication part. So within the same environment, we can do experiments and understand if some solution could be more feasible than others. Before leaving the floor to my colleague, this is the third quantum computing research topic that we address, and it's quantum computing emulation. The idea is to implement quantum computing strategies on classical machines. Obviously, this is not feasible for a very high number of qubits, but today it's an opportunity, and also especially considering costs, because we can implement through these strategies machines that can be used in real application scenarios, like on-premises solutions and others, like the ones presented here. We developed through VHDL code language a digital architecture to emulate quantum computers. And also we have models developed in CUDA for GPU. And this only for the quantum annealing paradigm that is useful essentially for the optimizations. For what concerns the quantum gate model, we have developed a complete framework to implement quantum algorithms here. Starting from a digital architecture, a RISC-V-like architecture, to implement our quantum circuit, a software stack to translate the standard de facto language for describing quantum circuit, which is OpenQASM, to be compatible to our system, and also a software model for identifying the best parameters to configure our system. So I leave the floor to Antonio to let him describing the remaining research topic you have. Yeah. Thank you.
Okay, now I will present the other three research topics remaining. The first one is related to the quantum circuit optimization. In fact, our research group has developed a template-based quantum circuit compilation toolchain, and which can support the technologies like NMR, trapped ions, and superconducting qubits. And another important work in this case is the layout synthesis for quantum circuit, which is integrated in the quantum compilation toolchain and is capable of supporting also the quantum dots. Moving on the other important topic, which is the quantum circuit design, we have developed two main libraries. One for the arithmetic circuit, for which we developed a software library which can interface the most important quantum computing languages, just like Qiskit, Cirq, and Ticket. And another important library is related to the unitary matrix decomposition, for which it can be seen as an automatic infrastructure for synthesis of quantum circuit, and is capable of decompose the quantum circuit starting from their description using unitary matrices. Moving then to the last topic, that is the one that I preferred because it's the one in which I worked personally. is the high-level software application, and in this case we evaluate also the application in which quantum computing can be applied, just like quantum image processing, in which it is possible to transform some image, do some process for the image using a few number of quantum gates. The main problem is related to the encoding of the classical data into the quantum circuit. Moving to the QML, that is the research in which I've worked personally, in which I worked on the variational quantum circuit and on the quantum support vector machine, in particular on the quantum kernel function. And then the last one is the optimization, in which our research group developed a toolchain for simplify the number of variables for the QubiTo, and also it was a study on the Grover adaptive search. Also, which are the use cases that our research group have been evaluating during these years? Well, there is the joint transmission, which is a technique for the multiple input, multiple output communication in collaboration with Team SPA. Then the optimization of urban traffic with Team SPA and Darwin. And also the optimization of virtual network function embedded problems in collaboration, in this case, with Darwin and Politecnico di Milano. All of these problems are solved formulating the problem as a quadratic unconstrained binary optimization problem. And these are our research. In particular, in green, you can see the main, the hot topic in which we work today. And if there are any questions, you can contact us also for the thesis.
Okay then, this ends the event for today. I hope you enjoyed the presentation of our speakers and that you learned something, that you will go home with some new knowledge. I just want to say thanks to all the people who contribute to this event. I want to say thanks to Edoardo Giusto and Lorenzo Bergadamo. I want to say thanks to Giacomo Ranieri from Intesa San Paolo. I want to say thanks to Bartolomeo Montrucchio, to Darwin and Links and that presented the research topics. I want to say thanks to all the people here from HKN that allow this event today. And most of all, I want to say thanks to all of you that you're here and that you showed a lot of interest in this event. So thank you very much, and I hope you enjoyed the event. Thank you.
And we want to thank Antonio Marceddu that helped us organizing this whole event. So thanks, Antonio. We give you an applause. Thanks to Davide, our events area manager, and the communication area that helped us publishing this all in Politecnico. And thank you all and to be here. We of ETA KNU open our recruitment in next semester, so maybe October or half of October. If you have any question about our organization, you can go to the table you can find near the door, and you can ask to everyone as our badge or our t-shirt. They can help you and give you some information. Thank you.